Picture this: a freight train weighing 15,000 tons. That's roughly 300 fully loaded semi-trucks stacked together, thundering down steel rails at 80 miles per hour. The contact patch between each wheel and rail, just about the size of a dime. That's it. A dime-sized area of metal-on-metal contact supporting the weight of an entire city block, navigating curves, climbing grades, and somehow never derailing. By every logical assumption, those wheels should slip sideways, slide off, or simply crush through the rails. But they don't. Today, we're breaking down the physics that keeps thousands of tons perfectly balanced on two thin strips of steel. And I promise, after this video, you'll never casually watch a train pass by again. Let's put this into perspective. The Union Pacific Big Boy locomotive alone weighs 1.2 million pounds. Modern freight trains can stretch over 2 miles long, with each individual railcar weighing up to 286,000 pounds when fully loaded. A typical freight train today might have 125 cars or more. When you calculate the pressure at those tiny contact points between wheel and rail, you're looking at over 90,000 pounds per square inch. Pressure greater than what exists in the deepest ocean trenches. Imagine 600 cars stacked vertically, all balanced on an area smaller than a quarter. By all reasonable logic, this arrangement should be physically impossible. The metal should deform. The wheels should slide off. But railway engineering has somehow solved problems that seem to violate our basic understanding of physics. The solution is both elegantly simple and remarkably complex. This engineering marvel didn't emerge overnight. The earliest proto-railways appeared in the 16th century mines, simple wooden rails guiding horse-drawn wagons. These primitive systems experienced constant derailments and structural failures. The wheels would jump off tracks, the wooden rails would splinter under load, and the whole operation was painfully inefficient. The key breakthrough came in 1814 when George Stephenson designed the flanged wheel, a seemingly simple innovation that revolutionized transportation. This critical development marked the birth of modern rail guidance and set the stage for everything that followed. From there, railway technology advanced rapidly. The Stockton-Darlington Railway in 1825 became the world's first public railway. By 1869, the Transcontinental Railroad connected America coast to coast. Today, high-speed trains routinely travel at over 200 miles per hour in countries around the world. But here's what's truly remarkable. Despite 200 years of technological evolution, trains still rely on the same fundamental wheel-rail interface principles that Stephenson pioneered. We've refined and perfected the concept, but the basic physics remains unchanged. What once moved 2-ton minecarts now guides 15,000-ton freight trains using identical core mechanics. Railway stability depends on 4 critical engineering principles working in perfect harmony. 1. Conical wheel geometry. Train wheels aren't perfectly cylindrical as most people assume. They have a subtle taper that creates a continuously variable diameter. 2. Precise track gauge. The standardized distance between rails, 4 feet 8.5 inches in most countries, isn't arbitrary, but mathematically crucial to the system's stability. 3. Weight distribution. The massive weight of trains actually contributes to their stability rather than detracting from it, pressing wheels firmly against rails. 4. Carefully calibrated friction coefficients between wheel and rail materials, which must provide both adequate grip and appropriate slip. Think of it as a self-correcting mechanical system that fights derailment forces automatically. There's no magic involved, just precise geometry and calculated physics that create a dynamic equilibrium. The forces are constantly shifting, but always returning to a stable configuration. Here's where we demolish the most common misconception about train wheels. Most people think the flanges, those vertical lips on the inside edge of train wheels, keep trains on track. That's simply not true. The flanges are only an emergency backup system, a last resort that indicates a problem if they're regularly contacting the rail. The real explanation lies in that conical wheel profile I mentioned. Each wheel is tapered at approximately a 1:20 ratio, meaning the diameter decreases slightly from the inside to the outside edge. This creates an automatic steering mechanism through differential rolling diameters. Let me explain how this works. When a train begins to drift sideways on straight track, the wheel on one side rides up onto a larger diameter portion of its cone, while the opposite wheel moves to a smaller diameter section. Since both wheels are fixed to the same axle and must rotate at the same rate, the wheel on the larger diameter travels farther with each rotation. This creates a turning effect that naturally guides the train back to center. It's a beautiful example of contact mechanics, rolling resistance, and lateral force distribution all working simultaneously. The standard gauge of 1,435 millimeters was developed in relation to this tapered wheel profile to create the perfect self-centering system. The coefficient of friction between steel wheels and rails, typically between 0.25 and 0.4, provides just enough grip without excessive wear. When displaced laterally, the wheels naturally center themselves without any steering mechanism or operator input. It's pure physics at work, a self-correcting system that continuously fights against derailment forces. This elegant wheel-rail interface creates fascinating real-world capabilities. Take curves, for instance. When a train enters a curve, the outer wheels naturally find larger diameter sections of their conical profile, while inner wheels roll on smaller diameters. This differential rolling distance helps the train navigate the curve without derailing. Engineers enhance this natural behavior through superelevation, banking the track so the outer rail is higher than the inner rail. The calculation for this banking angle depends on the curve radius, train weight, and intended speed. Too little superelevation creates excessive wear and potential derailment risk. Too much makes slow-moving trains drift inward. Professional railway engineers calculate safe speeds using formulas that incorporate lateral acceleration forces, friction coefficients, and the unbalanced elevation of the track. Every curve on a railway has specific speed restrictions based on thousands of physics calculations. The same principles apply to grade climbing. The conical wheels provide predictable traction characteristics, allowing engineers to precisely calculate how much horsepower is needed to move specific weights up various gradients. They know exactly how steep a grade can be before requiring additional locomotives or reducing load capacity. All these systems include substantial safety margins. Beyond the self-centering wheel profile, the wheel flanges provide emergency guidance. Modern trains employ sophisticated derail detectors that monitor wheel position and track geometry in real time. If anomalies are detected, automated systems can apply emergency brakes before a dangerous situation develops. The precision required is extraordinary. Track maintenance crews use laser alignment tools to ensure rails maintain the exact gauge and superelevation needed. Even minor deviations can increase wear, reduce efficiency, and potentially compromise safety at high speeds. Every curve, grade, and speed limit represents thousands of physics calculations made by engineers who understand the delicate balance between these forces. It's a ballet of mass, momentum, and friction that's been refined for 2 centuries. Emergency braking presents another fascinating application of wheel-rail mechanics. When train brakes are applied, the friction between wheels and rails becomes critically important. Too much braking force can cause wheels to lock and slide, potentially creating flat spots on wheels, or even triggering derailments in extreme cases. Modern trains use sophisticated systems that modulate braking pressure to maintain the optimal slip ratio, just enough for maximum braking effect without locking the wheels. This calculation depends on wheel load, speed, rail conditions, and even weather factors like humidity and temperature. In wet or icy conditions, trains automatically reduce their braking efforts to prevent wheel slip. Sand dispensers strategically positioned above the rails can drop precisely measured amounts of sand between wheels and rails to temporarily increase friction when needed. The design of track components similarly reflects deep understanding of these physical principles. Rail crossings, switches, and junctions all incorporate geometry that maintains the critical wheel-rail relationship, even as trains navigate complex track arrangements. Switch points, the movable sections of rail that guide trains from one track to another, must maintain precise alignment to ensure the conical wheels transition smoothly without interrupting the self-centering effect. Even the rail profile itself is carefully engineered with a slight inward tilt that complements the wheel's conical shape. Load distribution across multiple axles prevents any single wheel from bearing excessive weight. A typical freight car might have 4 axles, each supporting approximately 35 tons. This distributed load prevents rail deformation while maintaining the precise contact patch needed for stability. Railway engineers also consider thermal expansion in their calculations. Steel rails can expand significantly on hot days, potentially causing track buckling if not properly managed. Expansion joints and temperature-specific installation techniques ensure the track maintains its critical dimensions, regardless of weather conditions. All these factors combine to create a transportation system of remarkable reliability. Despite moving billions of tons annually across complex networks, train derailments remain exceptionally rare events. When they do occur, they're typically traced to extraordinary circumstances or maintenance failures that compromise the fundamental wheel-rail relationship. The precision engineering extends beyond the visible components. The ballast, those rocks beneath and between the ties, isn't just there for drainage. It provides crucial damping for vibrations, helps distribute loads, and maintains track geometry under dynamic forces. Its angular shape and specific size distribution lock together to resist movement while allowing necessary flexibility. Railway bridges represent another triumph of applied physics. Their designs must accommodate not just the static weight of trains, but also the dynamic forces of acceleration, braking, and thermal expansion. Engineers calculate the resonant frequencies of these structures to ensure they don't amplify vibrations at typical train speeds. That 15,000-ton freight train balancing on dime-sized contact patches isn't defying physics. It's using precision engineering to work with natural forces in a remarkably elegant way. The tapered wheels, standardized gauge, calculated weight distribution, and optimized friction coefficients create a self-stabilizing system that has withstood the test of time. The real marvel is how 200-year-old principles still govern modern transportation. Despite all our technological advances, we haven't found a more efficient way to move massive loads overland than steel wheels on steel rails. The physics discovered by early railway pioneers like George Stephenson remain fundamentally sound 2 centuries later. Next time you watch a train pass by, observe it with new appreciation. That massive machine isn't fighting to stay on the rails. It's working with precisely calculated forces that make derailment practically impossible under normal conditions. What seems precarious is actually one of engineering's most reliable achievements. And now I'm curious about something else. Have you ever wondered how trains actually stop? The physics of railway braking will surprise you even more than how they stay on track. But that's a story for another day.